y'all. It's Dr. Know-It-All. I'm really happy to have Dr. Scott Walter with me again. It's been way too long, but it's been a little quiet on the robotics front recently until suddenly Dennis Hong and the RoMeLa Lab and also Boston Dynamics just came out with a couple of new videos. So we thought, let's talk through it, right? So anyway, how you been? Happy New Year.
Oh, yeah, I was going to say Happy New Year. It's the end of January here, so that's like almost the last day to do it. But also, happy birthday, John.
Oh, thank you.
Belated. It was yesterday, but we'll sneak that one in there. Give John the gift of a few more subscribes.
That's right. Yeah, everybody was really, really kind because I recorded that, and then of course I took off for the weekend. And I came back and checked, and I was like, "Whoa, that's a lot of subscribers." Yeah. So we're still trying to figure out what the heck to do for 50,000 because it's actually close enough now that I have to figure out what the thing is going to be. So something fun is going to happen at 50,000. So anyway, we wanted to talk about a couple of different things. Number one, Dennis Hong, if you don't know, is at UCLA and is head of the RoMeLa Lab that I can never remember what that stands for. It's Robotics Media Lab. Or
something like, or mechanics lab.
Mechanics lab, yeah. Anyway, sorry, I can never remember.
Or
but anyway,
mechatronics, maybe.
Yeah, maybe. Yeah, could be. Anyway, he posted something on Twitter on the 30th. So actually,
yes.
Today? Oh.
Now we have been kind of procrastinating and getting this video out because 2 weeks before that, I think, was it about 2 weeks before that or 10 days before that, Boston Dynamics came out with a new Atlas video.
Right.
So and now it's like, cool. Okay, we can do them.
We can do a little comparison thing. So let me share my
Tesla also came out with another, they tweeted an old video. Everyone thought it was like a new video of Optimus, but it's like, nope, we've seen that already about the actuators. So there's nothing.
Yeah, that was a little unfortunate. I was sad about that one because, okay, I just blew up the screen. Can you still see that? Like, is that in there? Okay.
Yes.
So I'm turning off the, Twitter's video. Elon Musk needs to fix that still. The video is still less than ideal. But anyway, I've turned off the sound for all of these things so that we can talk over it. And certainly I will leave the links to all of this in the description so you can go look at it yourself. But anyway, so you can see that this is a lower body test. He's actually, is he wearing Nikes? I don't know if he's representing.
Yeah, he's wearing some kind of training flats. I'm not sure whether they're the Nikes or not, but it's rather interesting that it's off the shelf.
So you were mentioning before we started recording that you noticed that this robot is constantly walking even when it's standing still.
Yeah, it seems very nervous. So even when it's not moving, its feet are kind of going up and down. And I'm assuming it's just because it wants to be ready for what's about to happen.
Right. Right.
It's this expectation I'm about to get pushed, so it sort of wants to have everything already running.
Right. and of course, with the legs being bent, there is a little bit of cheating involved. I always say it feels like a toddler walk when they're keeping their legs bent. So. Yeah, you can lower the center of gravity that way. But I mean, it is reacting really, really well to being pushed. And yes, this is part of the testing. That's what Dennis actually, he retweeted this today and said, look, if people are upset about this robot being pushed, it's part of the required testing to show that it's functional and everything.
It's stable, right? Because anything like this can sort of happen that suddenly, you have an outside force that comes in that's unexpected. And you need to see how quickly your control system can react. So that's what's really impressive about this is the fact that it has a kind of a planned trajectory, something it wants to do, and then suddenly something unexpected happens from the outside.
Right.
A random event, and it has to recover very, very quickly. Now, I found out about this tweet because it was then retweeted kind of to me and a bunch of other people, and I was really happy to be like one of the people actually in the tweet thread that was called out. And my reaction to that was, I love a controlled fall. I love watching a controlled fall. Only to see that Dennis and RoMeLa Lab like that reply, because that's cool. Pretty much the best way to describe what walking is. Walking is really just a controlled fall. Right. You're constantly falling forward. You're constantly falling down, and your legs constantly go right out in front to break the fall, and then you recover a little bit again, and you do it again. And that might be a little bit of what's behind the fact that the feet are kind of moving, because it wants to be in this continuous falling mode the whole time.
Exactly.
Even when you decide to inject the outside
and I mean, obviously for anybody who's lived, I'm sure everyone has tripped. And if you catch your foot on the back of your other foot, you go face first right into the ground. So, because you are always falling when you're walking. So one thing that's really interesting, of course, is this is definitely not Optimus. You can tell that all the actuators and everything in the legs are quite different.
Yes.
And I'm not even positive. I can't tell underneath the black sort of sock thingies, whether there are other
what's going on there
actuators down there, but it's really interesting because the two big ones at the hips are able to rotate in and out, which is very cool. So you can see it actually doing like kind of a
everything that's needed,
right? Which is super cool.
Everything that's needed to recover, and the whole thing is that you need to have your control system tuned to have the gains just right, that you are able to deliver enough power when you need to recover, but not overshoot.
Right.
So that's always the problem, is that if you have too much power, you're just going to make things worse. And if you don't have enough, well, you just tip over and you can't recover.
Right.
And so a lot of what's going on here is just sort of seeing how good that control system is. It's a very active control system. It has to recover very quickly. And that's probably is more of the test there than it is actually of any mechanics.
Yeah. I would imagine so. I mean, it doesn't look like they've, tried to work out some sort of super slick. In fact, to some extent, it looks kind of beat up on the thing, but
they all they all have their lumps, right?
Exactly. So the real world is a tough place, but yeah, you can see it. Like it's really fascinating watching it. The more I watch it, the more impressed I become, because I realize just how on every fraction of a second it's adjusting itself. And that one in particular, the one where it kind of gets shoved off axis and has to, it spread its hips and kind of like waddle a little bit to capture itself. I'll let it play back through that one more time, and then we'll move on to Boston Dynamics. But that one kind of comes out. But
because suddenly you're getting a push more from the side. And that's the only way to be able to recover it, as opposed to when you're being pushed directly from behind. Then just the feet moving forward will be enough.
Exactly.
But you get a blow that comes from the side, that you've got to be able to get your legs to kind of splay out a little bit to plant and then get the recovery.
I think this is it right here. Yeah, like that. Yeah, see where it has to do that splay out and correct itself. So anyway, very, very impressive.
And the other thing to notice is that it's not like it recovers in one step. It's trying to dissipate the whole problem that's going on there. Right. So it seems like the strategy is like, you don't fix it right away. You try to do something to keep yourself from falling down and get yourself into slightly more stable state, and then put something else down and gets a little bit better and a little bit better. And we're sort of used to that. If you look at any kind of control system, you try to get up to some level here and you're going up like this, and you kind of like, you overshoot, and then you have to get in and come back and eventually get in there. And John, what is that called? That when you go into your control system and you overshoot, you get that peak that comes up and goes back down and it wobbles back to it. Do you know what that's called?
I'm sure I do, but I'm just blanking on it right now. What is that?
You're absolutely blanking on that, huh? In control theory and Fourier transformers, when the Fourier transform doesn't exactly fit a step function, that little overshoot is known as the Gibbs phenomena.
I should have guessed that. I pretty much figured that had to be it.
Yes, it's the Gibbs phenomena, and that's what I refer to, like in the car with ego. That when the steering wheel kind of like does one of these things back and forth when it's trying to get itself straightened out, I'm going, oh, there's the Gibbs phenomena.
Have you noticed?
It has nothing to do with the way you drive, John.
Yeah, that's right. It's all about me. Have you noticed that it feels like that has the overshoot and the corrections in the turning has gotten better with the last couple versions of full self, at least for me.
Oh yeah.
It used to be there's a turn in my neighborhood where it was just like like that, making that turn. And now
I have a couple of roundabouts that are kind of small that it just goes through really smooth. Before it used to be, it was like definitely tessellating the curve, not the way you want to. And now it's like this really nice spline that's going through. And then I look at that, and then it was good about 2 or 3 releases ago, and then the latest one about a week ago, whatever that was, it's even smoother. I mean, there's still an improvement there. Yeah. And a few other places, and still some things that is like, oh, they still haven't addressed this issue and that issue and a few others, but it's improving.
Yep. And all of us, just to throw in another preview for version 11, that what do we have? The Phantom release. What was that one today? It was like something like Indiana Jones and the Lost Software Update. And the Lost Software Update, exactly. So eventually, I hope we are all going to get ourselves version 11. But in the meantime, so let's go ahead and let me show the Atlas Gets a Grip, which is this is the finished video. And I think this is actually in some ways the least interesting video, but it's just so that people get a sense of what's going on here. Yes. But then they have a couple of behind the scenes that are great. So anyway, this guy's like, oh, I need my tools. I need my, Atlas, come get me my tools. So there's Atlas.
Okay.
But one big change here is that he's got grippers now. So
Yes. So
Interact with
he's
the
able
world.
to actually grab and interact with something like that.
Right.
Put that up there. So, this is all very good. Like the apprentice is doing what they're supposed to here. He seems to be very eager to help out
right.
the boss. Okay.
And that, by the way,
up.
that is a soft bag. I mean, it's fairly full, but that is soft. So that requires some dexterity to pick something like that up.
Got some tools, right?
And then
that's nice. That platform is not stable. Oh, did we miss that? That just kind of glitched on me there. The way he threw it up there. As soon as I saw that, I'm like, oh, as soon as he does that, it's like, there's probably like an OSHA violation there. And that's
I know, right?
right there. And there's the second firing offense right there. Okay.
Yeah, no dismounting through flips. Yeah. So I think that where was that? This, by the way, I mean, this is actually very cool because when you see him run across the stuff, the board is it bends.
It's moving.
And all of this stuff is moving.
Scaffolding is not as solid as you think.
Right.
Now, this here, that is like
was the ocean. That's an ocean. Throwing.
You'll get a dressing down from the boss on that one.
And by the by, right here, this is a multi-axis flip, which is the first time they've ever done one. So they're very proud of themselves. Yes. They talk about that in the behind the scenes.
Yes.
But
yep, they do. Yep. They call that the sick trick.
Yes, exactly, which I really like.
But I guess the other thing I'll say about that trick, I mean, anyone that's done diving, from a board or gymnast or someone who's skateboarding or snowboarding, these things all have names.
Right.
And I'm surprised. So evidently there's like absolutely no one on staff there that either has kids that were divers or gymnasts, or they didn't think to go out and consult one. Yeah. Because those flips are known. And so they just call it the sick trick, and they wouldn't even tell you exactly what it is. It's a forward one with a half twist. Okay. It's as simple as that from the straight position. Okay. Because they get the forward somersault. I mean, I can tell you on the dive program. It's like,
I thought there was like, isn't there like a gainer or something like that?
1021A. That's exactly what that is. If he was going into water. All right.
Well, there you go. I'm a little bit surprised actually that they don't have a dive consultant or a gymnast consultant,
because it's exactly what they do is if you notice how he does the crouch and how he has to go in there, if you just bring in a diving instructor, they know exactly what you have to do and how you prepare for a somersault, what you have to do for a twist.
Right.
And when my son took diving, the first day, the diving coach handed us this really thick, small notebook with like all these different things and like discussion of Kepler's laws and all these other things, because it's like they understand the physics behind what's going on. And the reality is that once you take off, you have absolutely no control on what's going on. So everything is on the takeoff. Once it happens, you don't have any RCS thrusters or anything like that. Control yourself. The only thing you can do is like change your inertial properties a little bit.
Right.
And that's what they talk about, the famous thing, like pulling the arms in like a figure skater to get you to spin out a little bit faster.
And you can see that when he does it, because he tucks and then extends his legs to slow down the rotation before he hits.
Yeah, and that's the classic thing that you try to do to stick to the landing. And what anyone who's doing a somersault, what the divers do, believe it or not, they're not like closing their eyes and just like spinning around. They are actually looking for reference points on the horizon or up on the ceiling or something like that. They know exactly where they are on the roll. No matter how fast that thing is, they know where they are. And they know if they're over rotating or under rotating, and they know when they need to kick the legs out. Because that's the only thing you can do is you can kind of control how fast the final rotation is to try to stick that. But you've got a little bit of wiggle room in there. But once if you really take off wrong, forget it. It's a flow.
Yeah.
And that's why they have to simulate the physics to figure that out. And that's what becomes a challenge, because the inertial properties of that robot is probably pretty hard to calculate. I don't know how.
I mean, and it's got it's got a lot of top heaviness. Yeah. I mean, I'm sure they can weigh each element of the robot, but then they have to know what kind of torque and what kind of forces they can apply, the maximum forces at each joint. And let's let me share the screen up and away so we can watch this, because this actually is a sort of all the mistakes that were made, I guess.
This one is great. This one I like. I like the outtakes better because it really shows you.
And sorry, this is a short, so it's vertical.
When he tripped there, he really tried his best to recover.
Yeah.
So it was like there's a reflex reaction there to try to recover.
Right.
Even that one
he
there
took out a piece of wood. Did you see him take out that piece of wood?
Yeah, he took that out. And as I mentioned earlier, you see how they have to put them together a lot. So he's been put together more times than C-3PO. So
there you go. That's the line.
Now this one here is that. Look at that. Look at this. Look what's going to happen. His feet are going to slip off here. It's really slow, but still it's like, no, I got it.
Yeah. But also, did you see the one arm that was pivoting to try to balance itself right? So it'll play through again, but support thing. I know.
I mean, and that looks exactly like what a human would try to do to recover.
Yeah, exactly. It also looks painful because it looks like one of those crotch shots that would hurt really badly.
Oh, yeah, exactly.
Right there. Bam. He takes out a piece of wood.
Yeah, he almost had it. It's just that somehow the fact that the feet weren't on level ground threw him off a little bit. Didn't know quite how to recover.
Yeah.
But still,
all very complicated because right there, the arm like pivots backwards a couple of times to try to
kind of gets the recovery.
Which again, very human.
Yep, I'm okay. Oops, this kind of went off. Yeah, fine. And part of that reaction there, probably because the arms were going up, there was enough reaction force on there that caused that back foot to slip. And then you get that recovery.
Right. Poor guy.
Unfortunately, we can't fast forward that back and forth.
Yeah, I know. YouTube
shorts,
shorts are just not ideal for this kind of stuff. But anyway, it really does try. I mean, it like attempts to do that. It looks very human when it starts to fail because it looks like what a human would do to try to recover itself. So this is all very impressive, by the way. I don't know how to.
Yeah. Now a couple of things they point out is you got to remember is that if you take a basic class in physics, they talk about F equals ma, and it seems very simple. Everything is scalar there, kind of, or at least the mass is a scalar, and everything else might be a vector. But then when you get into rotational dynamics, it's kind of a similar formula, but it's no longer m. It's the inertia tensor or matrix,
right?
And that thing is very difficult to calculate for any sort of standard shapes like a cylinder, or square, and stuff, or a cube. It's fairly easy, but when you get an everyday object, it's pretty complicated. Even with CAD systems, and if you know the density of the material and everything, there's some heavy calculation has to go on to calculate it for every single part. Now, the thing is, as the parts come together, they form this much bigger mechanism, which also has an inertia, which is made up of all the inertias of all the others. And it depends upon the configuration that they're in at any instant. So when you start moving the arm, suddenly the inertia matrix for the entire system now changes. And you have to know how it's changing as you do it. So that, and if you remember the parallel axis theorem and ever having to do that and how difficult that was, it's like it's that on steroids, because it's not just two bodies, but these multiple bodies. And you need to kind of know that to be able to calculate the physics right. And if you get that off just a little bit, it's very hard to predict what is going on.
Right.
You can do it to some degree and some success, but it is challenging. So when they're doing those simulations, they're doing their best to try to figure out what does the launch force have to be and the angles and everything to get what we need. And they get a pretty good guesstimate, and then they go out and they run it. And then they see, oops, it's not quite there. He's broke. We got to fix him. We got to put it back together again, and then whoop, and try again. And then I wonder how much they calculate what the inertias are for all the individual links that they're putting together, and how much that they've been able to get actually empirically just by doing measurements in the lab to kind of find out. And you could do that to some extent.
I'm actually looking at this guy, and I'm thinking he has 10 major parts that have to have the inertia calculated, because basically his entire torso and head is one unit. I don't think that moves at all. So you've got
every rigid piece of body that moves.
Yeah. So so 4 for the 2 legs, 1 for this sort of hip area, 1 here, and then 2 for each arm, not including the grippers. I don't think they weigh enough to matter that much, but I mean, that's 10 of these things you've got to calculate. Yeah. It's 10 interacting tensors that have to, interact with it. That's crazy.
And you have all those things that you kind of know ahead of time, but then when you go and you grab an object, and that object becomes part of you, now suddenly you've changed your inertia tensor. Yeah,
that's true too. Because and this is a really good video. I figured we'd play this while we talk, but you can see him picking up. This is a heavy object, so this changes his whole center of mass, and that's, I assume, a heavy object. These POV shots are really fun. I really like that when you can see, like, especially when it flips. But then it also, in some of this parts, they show him picking up like weights, like bar weights, which are substantially
heavy.
That's
what it's going to kind of point out. It's not just that they're heavy, it's the fact that they're not a point mass.
Yes.
So the easy
Yes.
way to think of that barbell is like, oh, it's just a point mass. And that's how we
Right.
simplify it, like that right there. So what you can do is you can say it has a center of gravity, right? And
Right.
so all the forces are going to the center of gravity, and we just take that mass and we put it there. It's like, you could do that, but it's kind of a shortcut, but
Right.
it's going to throw you off, because the fact is you've got two 50-pound masses that are kind of like to the left or the right of you,
Right.
that are going around, and that's the inertia that is causing you the problem. It's why you cannot think of it as a scalar property, but you have to think of it as this tensor property.
Right.
And that as he's running around on there, that is what kind of causes him to tip to one side.
Yeah.
He could have taken that same mass, and if it was concentrated right in his middle, he would not have fallen over. But the fact that you've got that kind of on the outside is like, whoa, that's just going to give you that little moment that's just going to cause you to lose your balance. Right. And that's something that the control system would like to know about, because if it knows about that, it's a lot easier for it to understand what can and cannot do and not attempt to do something. So we know we can all run at a certain speed.
Right.
And we think, okay, I'm going to run at that certain speed. But if we now put a really heavy backpack on you, suddenly, wow, it's very different. And you realize you've got to change your stride and everything else. It has to try to do the same thing. And how do you inform that? Does it just suddenly realize, I feel a bit sluggish here. I must be carrying a really heavy weight. Or you kind of tell it ahead of time, like, guess what? You're carrying something heavy. You might want to take it easy.
Yeah. Yeah. I'm trying to find, like, there's a spot where it shows, so this is a lighter weight, obviously, but there's a spot where it shows it running with a heavy weight and then it tips over because it wasn't.
It tips over.
Properly,
yes.
So.
Yeah, it tips over. Or it just, all it took was just that little bit of a tipping moment one way or the other.
Right. Exactly.
That it may have been just a little bit off center one way. It didn't quite grab it right. So it was like a little bit more to the left and then a little bit to the right. Now, the thing to point out, the big difference between Atlas and Optimus is they're very different use cases.
Right.
And if when you're an engineering student, you first take your classes in statics, and statics are fairly straightforward, where you learn how to figure out whether my bridge is going to fall down or not. All your forces are static, there's no movement, and you can almost do the calculations by hand. But the dynamics is that when you start having a lot of motion and movement of things, of forces that are no longer static, but they are constantly moving around and becoming very dynamic, and that becomes a lot more challenging to do. The thing is that so long as you're not moving very fast, you can kind of cheat and almost pretend your system is static. But once you get a certain velocity, it then truly becomes dynamic. And Optimus is kind of in that range. It's like, well, there's a little bit of dynamics here, but it's not a whole lot. So it's a lot easier to kind of manage it. But you see, the name is in the company. It's right there.
Exactly.
And so they need to know that. And you definitely are going at velocities there where dynamics become very important. They contribute.
Here it is.
Forces and
torques. And boom,
right there. And then suddenly it's like, whoa.
Oh, and I noticed this is also the most replayed moment. So that's the spot where everybody went back to look. But so this is the thing where you can see, like, the fact that you've got these there's a moment arm to that, and and it's just hard to fight it. The thing is, he's tipping, and right now his pivot is on that foot, and that's the foot he needs to extend out to try to break it. The problem is he can't get off the foot because there's just too much weight on it. And so I mean, they may have.
Okay, what can I do here?
It's when he collapsed. It's like he just went bang. Like it was the whole thing. I assume that there just wasn't enough torque on the motors to be able to correct for it. It was like the
thing that surprises me is they don't have some sort of reflex reaction in there, like a fetal position that it's going to know I'm tipping, I'm falling over, and just automatically get yourself into that tuck and roll. That's the first thing. Like what do they teach you, especially the newbies? Us Gumbies, when we go out climbing with you, John, to a bouldering gym, the first thing they do is they show us how to fall. How to fall well. They will not let you climb there until you can prove to them that you can actually fall correctly. And that is, crouching in and being able to do a very simple somersault.
Right. But on the good end of things, it doesn't do the classic human mistake of putting your arm out, which breaks your wrist often.
Oh, the thumb. That's the most common in ski areas. They say that's like the most common injury.
So you just catch it and
Oh, it's a name for it. It's called like a FOOB or something like that. Or there's actually an acronym for it. I have to ask him. My ski patrol buddies. Oh, what was that called again? But that's a very common accident.
Oh, he tried. So again, you can see where it just miscalculates the I mean, these are very, very complicated. Now, for anybody who's asking,
that's a good move right there.
Oh, it is. But this is a fantastic move too. But it's got too much weight, so it couldn't get the upper torso up.
You know, they were trying to do, and that kind of would have been clever.
Yeah,
they're trying to take that weight and pull it right into where is the center of gravity of the system when they go up,
so that it rotates.
And then almost using the weight as a way to help them pivot around.
I did see that. It kind of raised the weight up and tried to pull it down to like give it, which is, I mean, I think that's what you do when you do flips is you often use your arms that way. So you kind of throw your arms down.
Your arms are very important for that. Yep.
Right.
To get the reaction that you would want to have. Yeah.
Right. So,
and,
I mean,
cats are really good at that too.
Yeah. I think on one thing to be very clear with the audience is that if you think that this robot is making this up as it goes along, it is not. They talk extensively about how they script this. They use a physics simulator to like go over and over and over again to try it out and try to figure out how to make it work before they even throw a real robot at the whole situation. So
yes,
you know,
yes.
So one of the things
later on,
one of the tools that they really have here is a simulator, which has got to be an excellent simulator. You know, it's really good at simulating all the physical properties of what's going on.
Oh yeah, because all the physics that you need is, you know, when you're pushing off a surface, you need to know is that a compliant surface or is it a rigid surface? What's the coefficient of friction that's going to be there? If you don't get those right, then what you end up getting out of it in the air is a little different. That's why it was interesting to see, you know, everything they're on is not very rigid. That scaffolding is not rigid. That's plywood.
No. And that's the part that like impressed me the most was that I actually just realized what they should have is like a demo of Atlas should be ice skating. I think that would be an impressive demo for it to have its balance and to be able to understand almost zero friction, you know, very, very low friction surfaces would be really, really cool. So
might even be worse. I mean, sometimes friction is your friend. I mean, in a lot of things.
Oh no, that's what I'm saying.
As much as we try to get it out of systems, a lot of times you want it actually in your system. Yeah.
Well, I mean, most of us adults can walk, but not very many of us can ice skate well, you know. So I love. I guess he's doing Donkey Kong or something. I don't know.
Yes. Yeah. So you see, it was in the simulator, and now they're trying to get it to do the same thing, and then probably looking at the feedback to see how much that actually matches what they wanted it to do.
Right.
And, you know, they had some encoders in there that went bad previous that they had to replace. And, you know, that's very important. You know, if the robot does not know where it is, it's not going to be able to continue the execution.
Right.
And that's what I sort of wonder when they do that flip. You know, the human is using their eyes. I don't know how much they're using like their own, you know, internal IPU. To figure out where they are. We have a slight sense of that, but the robot would have that. So I wonder how precisely it knows where it is in its role, so that it knows when to kick out in order to stick the landing, or whether it's just based purely on time. Because if you do it on time, that just means that you took off exactly the way you expected. Right. And if there's any error, then it's very hard to correct.
The interesting part about this is, and it looks like they're doing a lot of this based on time. And we just happen to be watching that part of the video right now. But if that's the case, then how does it know like that recovery when it actually strikes the pad?
Yeah, well,
that's got to be updated.
You get the
real
planning
time.
phase, right. You've got the planning phase, and the way to think about it is that if you're going to go on a trip somewhere and you're driving from your house to Atlanta, and you know that you've got some milestones along the way that you expect to pass at a certain time. And so long as you're hitting it at that time, you know you're going to make it to your meeting on time. But now suddenly, if you're a little bit behind, that means, the next milestone, I got to speed up. I've got to I've got to go a little bit faster in order to make it. If you're doing fine, you might be all right. And of course, if you're way ahead, you might say, I can slow down, be a little bit chill here and take it easy. So what they do is they plan a trajectory, and they know exactly where they need to be at every single millisecond along the way. Right. And then they're constantly measuring to see how close we are to that. And if we're a little bit behind, then they try to do something to speed it up. And if they're a little bit ahead, then you try to do something to slow it down. That's exactly the whole idea of a control system, is that you're trying to match that along the way. And if you get too far off, then you're injecting a lot in there. You get these high gains, and that's when a lot of times you overshoot. Right. And so the problem can be is if you plan a trajectory where physically it's not going to do that, it's just going to deviate right from the very beginning. Your control system is working really hard to get you back on what it thinks is the planned trajectory. So the better that you can model the physics to understand that if we inject these forces into the system because we actually know we've modeled it, we've modeled the inertias just right, that we know this is where we expect to be at every instant in space, then we know we're on target there. Now, if you change your inertias, like, he starts to suddenly pick up a box and I'm going to do this jump with a box now. We have no idea how much the box weighs or anything, and you try to do it, then you're going to be way off and you're going to have to somehow correct. So assuming you don't have that, and they've modeled it really well, as you're going through the air, like I say, the only thing that you can do to control your spin rate is to change your inertia. And you do that by either pulling in or pushing out, and then sometimes getting that leg kick. And that's exactly what a diver will do and gymnast will do to stick it, is that they see where they are, they know where they are, and then they kick out.
Right. And so it is an interesting combination, because even though all of this obviously is scripted and they actually had an animation engineer who designed the animation, so clearly it's all there. But as you say, it's got its IMU and probably also its sensors and things like that. And every couple of milliseconds, it's updating its status and saying, am I good? Am I in the middle of it? Am I too fast, too slow? Things like that. Adjust speeds as it goes.
Right. And they also have to know the angles of the arm. So they get the one thing that's probably just telling it where the center of gravity or where the center of the whole system is that they're measuring. Right. And then, that measure, they said that X encoder was gone. Well, that's really important. If you don't know whether the arm is at this angle or that angle, it's pretty hard to be able to know, where does it need to be for me to change my inertial properties.
Yeah, they actually, I noticed that was something that was a complete showstopper. They were like, we don't know where the x-axis of the rotation is.
It's like driving without a speedometer. It's like, exactly. I have no speedometer now. It's like, boom, okay. It's
like, well, we better fix that before we decide to do it. So anyway, it's very, very cool. Up and away. Can you see this when I just switch this over to this other one or not? Yes. Yeah. Okay. So let me see if we get to the right spot. It's that one where it actually puts its arm backwards, which tells me it's doing things in real time. And actually that one too, that we just did, because it's having to compensate for making mistakes. It's not quite there.
Yes. So they're giving it a task.
So there where it was like doing this, that's not scripted. That's obviously
that's not scripted
to recover. Yeah,
that's exactly. It's so they have something else in there to make sure that it's able to maintain its balance.
Right.
So there's one thing is like, we want you to try this thing, and the other is that whatever the control system tries to do to keep it in the correct position.
Yeah. So again, comparing it potentially to like Tesla full self-driving, there's sort of the primary loop, which is don't hit anything. And that's the thing that's constantly updating. And so you can imagine. What did you see?
I was trying to think, did it trip because I think it actually caught its heel when it fell over the other time. I think what happened is that
it hit its own heel.
Yeah, let's look closely. I think something actually tripped it
when it goes back in again.
when it goes back.
Okay. Yeah, but so like again, the basic thing it's doing is stay upright, don't fall down. So that's probably this little internal loop, and whatever you have to do it. And then external to that is like, okay, walk over here, pick up this bag, do these things. And so it's got the two competing dynamics of it going on. So let's see if we.
So right there, let's see this.
No!
It
actually did. It crossed its ankles.
It crossed its ankles.
Yeah, a classic skier's mistake.
It really is a klutz. Yeah. Okay, that's what it was. It tripped itself up.
Right.
Okay.
I appreciate Boston Dynamics for putting up. It's actually more. It's in some ways more valuable to see this than it is to see the completed project.
It's far more impressive to see really what has to go into it, and you can see that. No, this was not CGI. This is really something they had to work on. To get this mechanism to do that. It's also impressive to see what RoMeLa was doing, and the other thing is like Tesla just don't keep releasing old videos. We know, give us something new to work with. Come on.
I know. I feel like, come on, Tesla. Yeah, I was actually really excited when they released that video, and then I went back and watched it versus the original one.
I didn't have to. I was like, deja vu.
Well, I mean, I just wanted to make sure there was nothing new that had stuck in there, but it was the same.
The problem is I had looked at that other video, the initial release frame by frame so many times. It was like, yep, I've seen this.
Yep. It looks identical. So, but anyway, so I mean, obviously RoMeLa Lab is a university lab, so it's not quite the same level of polish that Boston Dynamics has, but it's also really, really valuable work that they're doing. This is it's multi-axis recovery, which is really cool. And I'd seen that with Boston Dynamics. They've done that before, where they had the guy with the hockey stick poking, the Atlas.
Yep.
But yeah.
Yes.
So
yeah. And I'm sure we'll see eventually something like that for Optimus. Is going to have to go through a similar test. And I guess anything else you want to talk about to finish up?
I don't know.
Some connecting the dots.
Oh yeah, I actually. So what do you think about well, first of all, Project Highland? I think that was brilliant on his part.
Yep.
I did not realize that the one before Le Rouge, so this was the original Ford fact. This was connecting the dots. Great video that came out 2 days ago. Yeah. Anyway, but
yes.
Anyway,
actually, I think it was yesterday. I think.
Oh, okay.
Today's Monday, right? Yeah, I think it was yesterday. Yeah,
I had my birthday weekend and took the weekend off, so I kind of lost track of when things came out.
It's a blur.
Yeah. No, yesterday was very slow. Saturday was a bit of a blur.
That's
yesterday
right.
I just kind of sat on the couch and did not much. So one time per year I can do that. Anyway, but yeah, it was fascinating because so Highland was the original Model T factory that Henry Ford put together, that they figured out all the mass production tricks, and actually I didn't have any idea about the way that the train would come in and they would actually like move 6 floors up and put all of the materials in the buckets. Anyway, so yeah. And you could get any color you wanted as long as it was black, because that was the only one that dried fast enough. That was the reason why.
Yeah, so, that's true. The other thing was interesting, of course, is coming up with the speculation that it will be the Model Tau instead of the Model T, almost an homage to the Model T, but you can't use the Model T because Ford already owns the trademark on that.
Yeah.
But there were some other interesting tidbits. Is that yesterday a lot of people were like chiming in on Twitter about this and that. And one of the threads was that something that Elon had tweeted out about a year ago, February 22nd, and that was tau is greater than pi. And everyone was thinking, oh, he's the Taoist now, all this other. Right. But what preceded that was actually the original tweet to that, because that was a reply to his own tweet.
Okay.
And he just tweeted out H bar.
Right. Which is Planck's constant divided by 2 pi. Yeah.
Or is it multiplied by 2 pi? I think it's multiplied by 2 pi. There's a 2 pi in there somewhere.
Yeah, I don't know.
Yeah. It's basically Planck's constant. Okay. So there's H, which is Planck's constant, and then you have H bar, which has got 2 pi in there. And of course, 2 pi is famously also known as tau, because there's a lot of people that think pi is not actually the universal constant. It should be 2 pi.
Right.
Or tau.
Right. Yeah.
And the interesting thing about, we all know what Pi Day is. Pi Day is March 14th, right? There is a Tau Day.
Yeah.
Tau Day is 6/28.
June 28th. Yeah.
What is special about June 28th? That is Elon Musk's birthday.
No, is it really?
Yes,
I did not know that.
That's his birthday. Okay. Now, when he was saying tau was greater than pi, it was like he was giving a hint. He was like H bar up there. It was like, don't think of it in terms of pi. Think of it in terms of tau.
Right.
Then what the H bar means, it means tau H, where H is Highland. Right. Tau is probably the model that's going to be in there. So you kind of put all those things in there and say, that makes a lot of sense to me.
And also Elon Musk is a huge fan of, I don't think Henry Ford personally, because he had a lot of personal issues, but what he did as a manufacturer was amazing. And he tried to get the Model E, and Ford said no. But every single one of except for the Roadster, all of the rest of them, the Model S, E, or 3, X, Y, are all Model something, just like the Model T. And so it would make a huge, and also the Model T was the first mass-produced car and was done. My gosh, when connecting the dots said they went down from 720 minutes per vehicle to 90. I mean, it was some insane.
Oh yeah, it was incredible. The amount of time that they lopped off it. It's like
right.
And if they're doing anything like that with Highland, then it's like, man, game set match. It's like no one's going to be able to keep up with that. If they just get like a 10 or 20% improvement, that'd already be remarkable. But if they get like an order of magnitude, that would be absolutely shocking. to be able to do something like that. I'm not sure that they could do something like that. If they do, they've got some sort of alchemy going on that nobody understands.
They've got the elves working.
I think the interesting
background.
thing about that is that when people were sort of like, oh, you know, Elon's tweet here about Tau great, I said, oh, is that something he just did? And it's just like, oh, that must have been something he did today, because he had already tweeted out, what was it, Omega and a couple other symbols. Everyone was like trying to figure out what that was all about.
Yeah.
And then when I realized, like, wait a minute, that H bar was back February 22nd. So they knew already back then about Highland. They already knew about Tau. That was already there. So this isn't some new project they just came up with in December or January. It's been around a while. Yeah. And
well, I figure by the time we hear about it, it's pretty deep into the weeds. Yeah.
They're very deep. They're very deep.
So the question is, are they going to build this? Well, there's a couple of things. I mean, at least Connecting the Dots says that he thinks that what they're going to do is use the Model 3 as a test bed to get it working faster before, which I think actually makes more sense, because before you do the Model 2, also Tau is very close to 2 in terms of like just the sound of it.
That's what some people think. Yeah, the Tau too.
Yeah. So anyway, so there's a lot of really good reasons. Maybe they'll have the Model Omega afterwards. Maybe that's why he posted Omega the other, or was that today? Anyway, that was like, Elon Musk tweeting green
Omega means the end also.
Maybe he just really likes Omega watches. Who knows? But he's always thinking about this stuff. So I'm very excited to see.
And he's always sneaking something out. So the question is it going to be released on Tau Day? Is that when they're actually going to have it there? Or is it like, because it's Elon's birthday, even though we know he likes all these different memes and doing things on particular dates, if they don't make the date, at least they can use the name, because the name makes sense since that's his birthday. And I think the only other thing I sort of replied to that when I looked at it, it's like, you know, we really are in a simulation in 69 days after 420 is Tau Day.
That's crazy. What in the world?
It is.
Yeah, we really are.
It is. There's just too many confluences of coincidences here. Like something is going on here.
So I don't know. We'll have to see. So what is your prediction for March 1st at Investor Day, which I'm still hoping maybe I'll get invited to?
My prediction is I don't get an invite.
Yeah. Okay. Well, I'm thinking that's probably likely too, but it feels like you think that they'll do maybe what they'll do is announce Project Highland as the Model 3 upgrade. But I really do. I mean, I love the idea that Project Highland is actually about the factory, not about the product. And so what they could do is announce a new factory that will build the Model 3 first and then other car, because I really don't think they want to roll out the Model Tau until they're pretty close to being able to sell it. Because the Osborne effect is going to be brutal on that. And you don't want to announce a $20,000 car and say it'll be here in 2 years. That would not be a good thing. So
and I think it makes sense to make it kind of based on the Model 3, because that's your simplest platform as far as complexity and everything else you want to go in there. So the whole idea is removing parts and processes as much as possible. So start with what is really the most basic one, and see if you can just absolutely knock it out and not worry about any sort of frills or anything else that would be in there. Just what do you need to have a car that is functioning and is street legal and safe?
Yeah, safe. I think that's an important factor, obviously, for them. But I mean, again, I'll go on the record saying I think it'll be single motor. You can get any color you want as long as it's stainless steel. And I mean, forget about paint. It really is. Paint is a huge waste of time. It takes so much. I think it takes as much time to paint the car and let it dry as it does to build the car. I think that's the kind of order of magnitude of.
It does. It's hours, because you have to go in and you have to paint it, and then it has to go and through the ovens and everything else. It takes hours and hours.
Well, and then if you want to do multi-coat, you've got to do that multiple times. So. So everything is multi-coat. You've got a primer. I think maybe a couple layers of primer. Then you've got the color that goes on there, and you got a clear coat that has to go on top of it. So you'll have quite a bit. And that does take time. And then sometimes they get messed up, and it screws up the whole production schedule. It was involved in some of these projects of seat manufacturers where they're trying to do just in time with the seats. And so they produce the seats only as they're needed, and that's based on what's going on in the production line. So when a car hits a certain point in the production line, they get a signal, build the seat. Yeah.
because in 7 hours, we're going to be ready to put it in there because it's going to go through the paint shop and everything else. So they have 7 hours to get that thing, put them in the back of a truck in the correct order, drive the truck there, which will be a half hour away, unload the truck at the right spot, inject it into the conveyor system. So the right seat shows up in the right place at the right time with that vehicle coming on down there. And
it's crazy.
They were trying to cut it pretty close to, I think they found that 3 hours was cutting it a bit too close. They had to push back to about 7. Just because there was too many other variables of things that were going on. Ideally, the whole idea with just in time is you have no warehousing.
Right.
You know, the only warehousing is the parts that go into the seats. You don't want to build the seats and then have to put them back in a warehouse, something like that. So what is it? We just build them, and the warehouse is the truck. We put it in the back of the truck, and the highway is part of the warehouse as well. And then you go there, and that's it. And if you get it going right, it can be really fast. But if there's any hiccup on the system, you need a buffer. And sometimes a buffer can get, you know, it means like, wow, we got to find a place for 100 seats, 200 seats, 500 seats. You know, where are they going to go?
The seats just keep coming.
You got to slow it down. So
but I mean, again, Tesla has the major advantage, which is that they've also reduced their seats. I think all Model Y and Model 3 seats are the same. And then I think the new Model S and Model X are, at least the front seats are the same for the most. Anyway,
this one supplier that they had, if you actually looked at all the variations in there, and I think Corey had kind of mentioned something like this also in a tweet like a week ago, the different combinations of seats that you could have, the matrix was like, there was a million possibilities.
Yeah. And you just don't want
do you really order that many, you know, between, you know, leather, heated, power, you know, the color they're going to have in there. And you just go on and on down the list. And that some of them get a little bit smarter and just said, there's only going to be like 7 types and that's it.
Right.
So your production schedule gets really confusing because you're going to have all these lines that have to be adaptable. And one case where they were putting the seats together, I think there were about 20 different stations that were sort of manual stations to put everything together that would be coming in from the sub-assemblies.
Right.
And one of them had a cycle time as low as 29 seconds.
Oh, gosh.
And as high as almost 2 minutes, depending upon the seat type.
Holy crap. Yeah.
The others were more balanced. The others were like, anywhere from 30 to 45 seconds. But
but you can't
holy cow.
You can't.
And so what ends up happening is you don't have a buffer big enough because that one is like right in the middle of the production.
Right.
And suddenly this order comes in for, you know, like you probably wouldn't be a fleet because this is a high-end seat. But there might be something that some family decides like, we're all going to get the same SUV. And so suddenly this line comes through. It's like, you got to build 10 of them in a row. And suddenly this poor guy is trying to do it. Because the whole assumption is like, like 1 in 10, he has to do it. It's not a problem. Most of the time, he's only doing the 29-second cycle time. This other one is really an offbeat one. So what they then have to do is they have to go through that production schedule and say, well, let's make sure that we don't have all of those come in there at the same time. We've got to spread them out.
Yeah. Yeah. No, that just makes every single one of those branching points makes things more complicated. So
because what will happen is if that person is sitting there taking a lot of time doing it, all the downstream processes, they're sitting there like, where's my seat?
Yeah, exactly. Where's the next seat and everybody on the other end is like, everything's backing
they're waiting.
up,
They're kind of waiting for that to come through. And so that will just starve all the downstream stations for that. So you're trying to keep it constantly in balance. And at most, you have one buffer in between to make sure that you're either not blocked or starved. So that you're not blocking someone, he can kind of push it out, and then you go ahead and go there, and hopefully your cycle times all balance out. And what you're trying to do, you're trying to make sure every station is roughly like 49 seconds or something like that for every single operator. But when you have them, it's like, whoa, up. And then, I mean, that is the ideal what it is.
Right.
And the person's having, and some of these are like, a guy goes in with a nut runner. It's like, okay, that's really easy. As a guy takes like some leather and he's trying to stretch it over this frame. He's like this big, bulky guy. And that's like all he does for 8 hours every day. He's like, putting him in. I was like, you mean to tell me he can do that repeatedly, you know, on his
at that speed,
40 seconds all the time. I was like, man, that's going to be exhausting.
Yeah.
This is going to be
a complete killer. Wow.
Yeah.
Wow. So what, given the fact that the Model Y is already a pretty darn efficient car to make, to cut that down by 50%, what is Tesla going to do? Because that's what Elon Musk said. That's what he said, whatever this next Model Tau or whatever it is. Well, like, what are they going to do to reduce it even
the front
more?
and rear castings. So you get the front and rear castings.
You think they'll do a unit casting? Do you think there's any chance that they'll just build the whole?
No. I think they'll be separate, and then you'll have the battery pack in the middle.
Okay.
So I don't think you'll cast it as one thing, but
I was imagining maybe casting it all as one thing, and then the battery would just have rails for the middle part, and you drop.
I don't think
it's
that would be
worthwhile.
that would be a huge press.
Well, that's why they have a 9,000 ton press that they just ordered.
I mean, maybe the two pieces would come out at the same time, but I don't know if they would be all together as one. But certainly you would do that, because then you eliminate the front and in the rear.
Right.
Just the fact that they're mounting everything on the battery pack and then putting that up.
Yeah.
So you have your skateboard with pretty much everything, and all you do is just drop the body on top of that. Some sort of exoskeleton or whatever.
And again, I mean, that's if you only have one
after
motor.
The body in white, it's the rest of the body in white. So they've got the underbody kind of figured out. What's going to be the trick to doing the upper part quicker? Yeah.
Well, and again, if they only have one motor, and they only have one option for like seating units and stuff. So again, just reducing complexity in terms of any incoming.
And then also think of the steering wheel. So, if you get fly by wire in the steering wheel, then suddenly all the mechanics, everything goes on. That's eliminated. That's true.
Yeah.
And that makes it a lot easier to install.
True. Okay.
So then I think the wire harnesses is that they've talked a lot about that, reducing the amount of cabling on that. So they may have ways of being able to do that, of almost having the wire harnessing practically built in a very early part to make it very easy. Certainly, well, I mean, you have your ground there. The question is, what else can you build very quickly and easily that won't be flexible? You get rid of the flexible wire harnessing and just get these almost these channels that you would put in, just pop in.
Right. Yeah. Okay. So reduce any kind of flexible parts, any kind of wires, obviously the number of parts. Again, the whole body in white thing. If they build it out of stainless, there's all of the paneling on the outside of the car goes away. Like all of that stuff is unnecessary. So
think about it. We spoke about this last summer when we first saw sort of it coming together, where they were mounting the seats on there, and the feeling that what you can then do is take the instrument cluster and it just kind of goes straight up. But you notice that when it went straight up there and they hung it in there, you still had people who are going in and going underneath and trying to connect all these connectors. Right. My feeling is like, just get rid of all the connectors and just have like some big plug. And when that instrument panel goes up, it just plugs in, and then the mechanical latches in, done. And no wires, nothing to done. So any harnessing, any weird wiring, that's done somewhere else, wherever the instrument cluster is put together. When that final assembly goes in there, you're probably like, just eliminate all the wiring, or as much wiring as possible. As much people having to crawl in there to snap something together. Just get rid of those fittings.
Okay. So I like that idea of just having kind of a huge connector that has everything you need. And as you move it up, it just pops in. There's a couple of plastic tabs that pop into place, and you're done. So and I'm wondering why you have, and a lot of times probably the only reason why you have a lot of these extra cables dangling around here and there is because you have too many different options. Like, oh, the person might have this particular thing or that particular thing. We need to have a connector for that. And maybe now it's like, well, we just have one connector. Everything is on there, and we just turn it on if we need it. Because if you remember the old days, computers, they came with like 16K RAM and 64K RAM, and it cost a lot more for the 64K RAM. And it turned out that actually both computers had the same amount of RAM on it. It was just a jumper cable. That was the difference. So you can just kind of go into
the tech to come out, and hopefully you're not looking around and going there like, just change it. And it's like, ta-da, oh wow, you put it in there. Oh yeah. So you build all those stuff, and we're already seeing that, like the performance package or something like that. That's a software upgrade. It's not that they have to. The hardware already exists. It's just
I think what they do is
now you get performance.
when they test out the motors, they take the ones that are the highest performing motors when they test them, and those go into the performance. But aside from that, the cars and then the brake pads.
But still, you can get a performance boost just through software.
So
I mean, it's the same thing. So they could have all the hardware just in there, and this is a question of turning it on for certain options.
Okay.
In the old days would be like whether you had air conditioning or not. So everything has air conditioning now. But I'm trying to think of some of the options that people may or may not buy.
Yeah.
And of course,
I'm thinking this car is not going to have a lot of options. I just don't see how you can build it efficiently.
Exactly, because I mean, in a sense, that's what the Japanese did, is that when they came in the 1970s and came to ashore to the U.S.,
Yeah.
They looked at what is it that consumers want, and we just put them in there, and that's it.
Yeah.
And in the US, it was different. I remember it was like you went down there. It's like, okay, do we get a power locks? Do we get power windows?
Right.
Do we get the air conditioner or not get the air conditioner? There's all these different options that you would go through. Yeah, they just build in Detroit, and it's here in a couple of weeks, so they can make all those different options of what you need to have.
Yeah.
Whereas in Japan, it's like all this stuff's going on a car. And we're just going to figure out what the consumers are going to want or not want, and they get this, and they're like, no, we're just going to produce them of like 1 or 2 option packages and just send them out there. And eventually, they just said, you know what, we're going to make all the windows power windows. We're going to make all the locks power locks, because there's no sense making manually. There's not enough people that want to do it. You just go ahead and figure out what that is.
Yeah.
And I think that's what the Tesla approach is going to be. It's just really figure out what 80% of the market wants.
Well, again,
make sure it's in there as a standard, and then forget about the rest.
The Model Y is the perfect example of that. You've got 2 options, and yes, you can get bigger tires and things like that, but that's stuff you just bolt onto the outside of the car in the end. But yeah, you get the choice of colors and whether you want performance or long range, and that's it. So
that's about it. There's no choice about the windows or the locks or the AC or anything like that.
Yeah. So yeah, very, very cool. So, all right, excellent. Thank you. This was fascinating, and we actually got into more stuff than I thought. I thought we were going to talk about.
Yeah, I don't know. It's going to be 1 or 2 videos now. It's almost like a second video here.
It's all good. Anyway, thank you so much for spending the time. And if people have questions for us, by all means, we can always do a Q&A kind of thing where we can respond to some thoughts that other people have. And of course, hopefully, we'll get more Optimus videos soon so we can actually see what's going on.
Okay, so here, if Tesla is like a little bit upset that we didn't talk that much about Optimus, it's like, it's on you guys. He didn't give us any material.
Give us more stuff. We'll definitely talk about it. All right. All right, everybody have a good day. We'll see you later. Bye-bye.
Yeah, bye-bye.